Hello everyone, welcome to this video lecture of 19ScPhyU301. We have been discussing the first chapter, complex numbers. So far we have discussed these basic concepts of complex numbers, and we also have discussed powers and roots and exponential functions of complex numbers. To find different functions of complex numbers or to perform certain operations, it is always good idea to have complex number in the right form. For example, when we are finding out powers of complex number, especially the higher powers of complex numbers, it is always a good idea to write the complex number in exponential form. Similarly, when we find out the roots. Nth root of a complex number has n number of distinct points in Argand plane, and to find all these distinct points, it is important that we write the complex number in exponential form. But when we are finding out exponential function of a complex number, that is when we are finding out f of z such that it is e to the power z, then you always write z in rectangular form, or which is this x plus iy form. In this lecture we want to consider a couple of more functions of complex number. The first one are these trigonometric functions: sine, cos, tan, cot, sec and cosec. We will also discuss hyperbolic functions. We will define hyperbolic functions and then we'll derive some relations. Let's begin by defining the first trigonometric function, sine z. So we have the function of complex number z, which is equal to sine z, and to define this we take help of Euler's formula that we have already derived. Let's write down the Euler's formula first. So e to the power I theta is equal to cos theta plus I sine theta according to the formula. Similarly, I can also write e to the power minus I theta as cos theta minus I sine theta. Let me call this equation as equation number 1 and this as equation number 2. Now if I subtract second equation from the first equation, so the operation I am performing is equation number 1 minus equation number 2, then what I get is e to the power I theta minus e to the power minus I theta is equal to 2I sine theta. And now this equation can be rearranged to write sine theta as e to the power I theta minus e to the power minus I theta divided by 2I. So this is how we can write sine theta by using the exponential functions, and by using the Euler's formula we can arrive at this equation. Now sine z is defined by using this formula that we have derived. What we do is we replace this theta with the complex number for which we are defining the sine function. Therefore sine z is defined as e to the power iz minus e to the power minus iz divided by 2I. So this is the definition for sine of a complex number. Previously, we have seen how to find out these exponential functions of complex number e to the power iz, e to the power minus iz, and all you need to do to find out sine of given complex number is perform this operation given by the right hand side of this equation. Let me erase this. So once again, this is how sine of a complex number is defined. Cosine z is defined in very similar way. Again, Euler's formula is used. E to the power I theta is equal to cos theta plus I sine theta, and e to the power minus I theta is cos theta minus I sine theta. So this is equation 1, this is equation 2. To define cosine z, now I will add the two equations, 1 plus 2, which will give me e to the power I theta plus e to the power minus I theta is equal to 2 cos theta, and therefore cos theta can be written as e to the power I theta plus e to the power minus I theta by 2. In terms of the exponentials by using the Euler's formula. Now you may have already guessed how we can define cos z. Cos z now is equal to e to the power iz plus e to the power minus iz divided by 2. So this is how you define cosine of a complex number cos z. In previous two slides, what we have done is we have defined sin z and we have defined cos z by using the Euler's formula. Sin z is e to the power iz minus e to the power minus iz divided by 2I, and cos z is e to the power iz plus e to the power minus iz divided by 2. So this is how we define sine and this is how we define cos. Once these two trigonometric functions are defined, then it is easy to define the rest of the trigonometric functions. Tan z is going to be equal to sine z divided by cos z. Cot z is equal to 1 by tan z, which, sorry, this is z, is equal to cos z divided by sin z. Then sec z is equal to 1 by cos z, so it is inverse of cos of the function cos z. This is sec z, and cosec z is inverse of sin z. So once sine and cosine, once these two functions are defined, then we can define rest of the four trigonometric functions. Since in previous lectures we have seen how we can find out the exponential functions, we all need to do is use that definition, use that method to find out the exponential function, and we can find out all the trigonometric functions of complex numbers. All it takes is some mathematical jugglery to obtain the trigonometric functions. Of course, the question remains that if we define the trigonometric functions of complex number like this, are they mathematically consistent? Although we won't prove it in detail, but the definitions of trigonometric functions in this way turn out to be quite consistent mathematically. To get a hint, what we will do is we will try to differentiate sin z with respect to z and let's see what we get. As the slide suggests, we should get cos z, which is true for real numbers. We know that. Let's see if that is true for complex numbers as well. So sin z is e to the power iz minus e to the power minus iz divided by 2I, and differentiating sign with respect to z here would mean that I have to differentiate these exponential functions. 2I is a constant, sorry, so 2I is a constant, I'll take it, and then we'll differentiate e to the power iz, which is going to be I into e to the power iz minus differentiation of e to the power minus iz is going to be minus I into e to the power minus iz, and therefore this is equal to 1 by 2I. I can take I common here and we'll get e to the power iz plus e to the power minus iz. Now this and this I will get cancelled and we are left with e to the power iz plus e to the power minus iz divided by 2, which is indeed equal to cos z, and therefore we can write that d by dz of sin z is equal to cos z. So we have proved that at least this equation of calculus for trigonometric function is true for complex numbers as well as it is true for real numbers. We won't go into depth of complex analysis in this course. We have to take as a fact that these definitions of trigonometric functions for complex number are mathematically consistent and they turn out to be correct for complex analysis. We will now move on in the lecture and consider the other kinds of functions of complex numbers, the hyperbolic functions. Hyperbolic sine of theta, I'll call it as sine theta, is defined in this way. It is e to the power theta minus e to the power minus theta divided by 2. Now this theta can be a real or complex number. However, the hyperbolic sign is defined in the same way. So even if I'm defining sin z, it is going to be equal to e to the power z minus e to the power minus z divided by 2. So this is how hyperbolic sign of a complex number or of a real number is defined. Note the similarity of definition of hyperbolic sign or sin z with definition of sin z. Sin z is obtained by this formula e to the power iz minus e to the power minus iz divided by 2I. So if we get rid of all these i's or the imaginary numbers in this equation, we get the definition of hyperbolic sign of z. So this is how hyperbolic sign is defined. Now let's define cos z or hyperbolic cos of complex number, which is equal to e to the power z plus e to the power minus z by 2. Even when hyperbolic cosine is calculated for a real number theta, it is the same way. It is e to the power theta plus e to the power minus theta divided by 2. So the definition stays same. All we do is we replace this real number with the complex number. So this is how sine and cosine z or hyperbolic sine and hyperbolic cos are defined. Now once these two hyperbolic functions are defined, we can define tan, hyperbolic tan, which we can write as tan h of z can be defined, which is equal to sin z by cos z. Similarly, hyperbolic cot z is equal to now 1 by hyperbolic tan z. Sec z or hyperbolic sec z is equal to 1 by cos z, hyperbolic cos z, and cosec z, hyperbolic cosec z is equal to 1 by sin z or hyperbolic sin z. Once we define hyperbolic sine and cosine, we can define rest of the trigonometric hyperbolic functions. So this is how trigonometric and hyperbolic functions of complex number can be calculated. This is how they are defined. Now what we will do in next slides is we try to derive some relations. Let's start with sine iy. So clearly here iy is a complex number. It is pure imaginary complex number, and we have to prove that it turns out to be equal to I into sine of y. Here we are saying that y is real number. So y is real. Let's prove it now. So to begin with, we write sine iy in exponential form, which is going to be e to the power I into iy minus e to the power minus I into iy divided by 2I. So this therefore is equal to e to the power I square y minus e to the power minus I square y divided by 2I. This is equal to e to the power minus y minus e to the power y divided by 2I. So here we have used the definition of sine of a complex number to write sine iy in this form. Now to go further, what I'll do is I'll multiply and divide the denominator by I. So sine iy therefore is equal to, after I multiply and divide this equation by I, what I get is I into e to the power minus y minus e to the power plus y divided by 2I square. But remember that I square is equal to minus 1. This is the fact that we also have used in this equation. To get this equation from the previous one, we have used the fact there also. So sin I therefore is equal to I into e to the power y minus e to the power minus y divided by 2. Now if you go to the definition of sin y or hyperbolic sine of y, this is exactly that function. Therefore, what we have proved is sine Iy is equal to I into sine or hyperbolic sine of y. Let's prove one more equation in relation with hyperbolic functions. This is the equation which is to be proved. So let's begin by writing the left hand side of the equation. Cos square z minus sine square z is equal to, now to write the right hand side I will use the definition of hyperbolic cos and sine. So it is going to be e to the power z plus e to the power minus z divided by 2, and this is squared, so this is nothing but cos z plus, or sorry, minus e to the power z minus e to the power minus z divided by 2, and that is squared, so this is sine z. Now what we need to do is we have to find out the squares of the brackets, so it is going to be e to the power 2z plus e to the power minus 2z plus 2 into e to the power z into e to the power minus z divided by 2. So here, sorry, divided by 4. Here I have simply used the formula a plus b whole square is equal to a square plus b square plus 2ab. Similarly, to square the second bracket, now I have to use the formula a minus b square is equal to a square plus b square minus 2ab. So if I use this formula, the square of hyperbolic sine z turns out to be equal to e to the power 2z plus e to the power minus 2z minus 2 into e to the power z into e to the power minus z divided by 4. This is equal to, now I can take 1 by 4 common. If we consider this term and this term, what we have is we have e to the power 0 in both the cases, which is equal to 1, and therefore this is now equal to e to the power 2z plus e to the power minus 2z plus 2 minus e to the power 2z minus e to the power minus 2z plus 2. Now in this bracket, e to the power 2z will get cancelled, e to the power minus 2z will get cancelled, and this turns out to be equal to 1 by 4 into 2 plus 2 is 4, and therefore we have proved the relation cos square z minus sine square z, or hyperbolic cos square z minus hyperbolic sine square z is equal to 1. So this is how we can prove the relation. We can use similar method to prove other relations involving trigonometric functions of complex numbers and hyperbolic functions. I encourage you to solve more and more problems to get the confidence in handling these kind of problems. Let's summarize what we have done in this lecture. We defined trigonometric functions of complex numbers. So f of z, which is sine z, is defined as e to the power iz minus e to the power minus iz divided by 2. To get this definition, we use the Euler's formula. Similarly, f of z, which is equal to cos z, now can be defined as e to the power iz minus e to the power minus iz divided by 2. Sorry, this is plus. So this is how we define sine and cosine of trigonometric functions, and from them now we can define rest of the trigonometric functions. Tan is sine by cos, cot is inverse of tan or is cos by sine, sec is inverse of cos, and cosec is inverse of sine. Then we define the hyperbolic functions. Hyperbolic functions, sine z is equal to e to the power z minus e to the power minus z divided by 2. Note here that you can replace this sign with a real number and the definition of hyperbolic function stays same. So sine theta is e to the power theta minus e to the power minus theta divided by 2. Doesn't matter whether this is real number or a complex number, the definition of sine z stays same. Similarly, cos z or hyperbolic cos z is defined as e to the power z plus e to the power minus z divided by 2, and that is also the definition for hyperbolic function of a real number. It is e to the power theta plus e to the power minus theta divided by 2. You can note the similarity between sine of a complex number and the definition of hyperbolic sine and cos. In this lecture, we have defined hyperbolic functions, but why are they called hyperbolic function is unanswered. So I am leaving that to you to figure out why the functions are called as hyperbolic functions. If you are taking the course officially, you will find a problem which hints towards the answer of this question. So that is all for today's lecture. In next lecture, we will see how to find out natural log of complex numbers too. So we will see how to find out f of z where the function is log z, natural log of z. We will also see how to find out z1 raised to z2. So how to find out complex powers of number. And third thing that we will do, third function that we will see in next video is the inverse trigonometric functions. I once again encourage you to solve as many problems as possible based on the trigonometric functions of complex number and hyperbolic functions and try to derive different relations involving them. That is all for today's video. Thank you for watching it.